Hello, thanks for joining us at the FKI Machine Coffee Seminar. And we have here online with us Pierre Wolinski. Yes. Okay, thanks. And so Pierre, he's a postdoc at INRIA Grenoble and the certified team. And he's been working on several projects that include, let's say, cover both statistics and machine learning. And I think let's say you worked earlier in a team which was doing computer vision. So let's say, so you kind of covered several interesting topics. But today in particular, you will talk about this Gaussian PreActivation neural networks, myth or reality. And yeah, we're really, really curious about this talk. And thanks for being here virtually. And I'll let you speak. Thanks.
So I'm presenting a work I did with Julien Armel about the preactivations in a neural network. So in a nutshell, we are studying neural networks here, which are models trained by gradient descent. And in these neural networks, the information propagates through a sequence of layers. So we have to initialize properly the weights and biases of a neural network in order to propagate correctly the information through the model. In many works studying the initialization on neural networks, the Gaussian hypothesis is made. That is, the preactivations are Gaussian at initialization. In particular, this hypothesis is not fulfilled in the edge of chaos framework, for instance, and can lead to inconsistent results. So the one aim of the work was to build a neural network where it holds. So we propose a family of activation functions and initialization procedures such that the preactivations are Gaussian. So here it's the very rough representation of one layer, which is a bit different than the usual because you have here the preactivation Z being transformed by an activation function phi in activations X, and then the linear, the affine layer outputting the Z, the preactivation Z. So more formally, the operation done is this one, where the Z are the preactivation, phi of Z is the activation, and W is the matrix of weights, and B the vector of biases. You can see here that we have a scaling 1 over the square root of NL, which is the square root of the number of inputs, which will be useful. It's a very useful scaling for theoretical study. I will explain later. So we train W and B by gradient descent. There are two potential issues. So it's 2010, not 20. First, we can end with the constant output. For instance, when the weights are too small. When the weights are too small, after several layers, the information vanishes. And we can have the contrary, that is the exploding output, when the weights are too large. In both cases, training is very slow or impossible at initialization. So the question is how to build a good initialization procedure. So here, in the framework we are in this kind of work, we consider that the weights and biases are random. For instance, they could be Gaussian with a given variance and for the weights and the variance for the biases. And we consider the inputs as fixed. It's not necessary to assume that the inputs are fixed, but it's better for the theoretical study, and we can generalize after. To find a good initialization, usually first we start by finding a criterion that the preactivations Z should match. For instance, impose the variance over Z. And then, after fixing a variance for Z, deduce a constraint over the distribution of W and B. So why do we want to impose a criterion on the preactivations Z? For instance, if the variance of the preactivation increases after one layer, then you will end with an exponential explosion of the variance of the preactivations. So basically, one constraint we may want to impose is a constant variance during propagation, or at least a variance that converge to something. And one way to attain that is just saying that the variance of the preactivations should be 1. That's a first heuristic. For instance, if we sample the W and the B according to Gaussian, we can tune sigma W and sigma B such that the variance at the end is 1. The first heuristic, naive heuristic, presented by Gloro and Deggio, is to preserve the variance of the preactivations. And in order to preserve the variance of the preactivation, so in a very specific case, the neural network is assumed to be linear, but that's a first heuristic. And as a result, in order to keep the variance constant, we may want to have a variance for the biases of 0 and a variance for the weights 1. So just for clarification, in the original paper of Gloro, it's a bit more complicated than that. And actually, we are working in this framework with a scaled version of the weights, with the scaling 1 over the square root of NL. So there is some differences, formally some differences with the paper of Gloro, but in the spirit, it's that kind of thing that happens in Gloro study. So this heuristic can be extended to an activation function such as ReLU by just taking sigma W square equal to 2 in order to compensate the 0 part of the ReLU activation function. So here we are with the first heuristics. Now in the presentation, first we'll study the propagation of the preactivations and the different heuristic we can get when we are doing the we are studying the propagation. We will see that in the edge of chaos framework there are some inconsistencies, and we show some counterexamples to some of the edge of chaos results. Then we'll propose a solution that is an activation, a family of activation function and a family of initializations distribution for the weights, and then we'll end with experimental results. So here, in this first part of this section, I will present the framework of the edge of chaos. So the idea is a bit more sophisticated than in Gloro and He heuristics. So we are considering not one, but two quantities. First, the variance of the preactivations. So in this framework, we are considering not one, but two fixed inputs, let's say XA and XB, and we are studying the preactivations when we are putting XA at the input and when we are putting XB at the input. So the variance VA means, VA of L means the variance of the preactivations at layer L when XA is an input. The second feature we are studying is the correlations between the preactivations. So CAB of L means the correlation between ZA of L and ZA of L and ZB of L. So the goal is to preserve the correlations between the correlation CABL during propagations. So why? Because when we are taking two inputs, XA and XB, we are introducing what we want is to preserve the geometry of the input space, for instance. I will explain why later. But when we want to keep intact the geometry of the input space, then we want that if xa and xb are very close to each other, then we want that the results, the successive results, the successive preactivations should be very close. And if they are very far from each other, then we want the correlations remain very far. So in summary, we can we may want to keep the correlations constant. So why do we want that? Because at the beginning of the training, we don't have any information about the way the input space should be modified in order to fulfill the goal. So that's the first heuristic we may want to have at initialization. But obviously, it will change after training. But at initialization, we don't have any information. So the solution found by Poole and Schanthaus was to find a recurrence equation allowing for computing CIB of L plus 1 in function of CIB of L. And then study the function f and understand at which condition the CIB of L is independent of L. But first, some approximations should be made. So in the recurrence equation for VA of L, the variance, this recurrence, I won't explain exactly the meaning of this equation, but the main things to have in mind is that there is an integral that is an integral over the preactivation, over the preactivations at layer L. And this distribution of the preactivation, dl, changes and changes during propagation. It's a problem when you want to do a theoretical study. So you simply remove that and say that the distribution of the preactivations is constant when during propagation. There is some heuristic behind it. I will explain that. But the idea is to preserve the shape of the distribution of the preactivation ZL is preserved. The chosen solution is D is Gaussian, because when you are using neural networks with very large layers, with that is with NL tends to infinity, you can use the central limit theorem and obtain ZL, which is Gaussian at any layer. And from that, we can build simplified dynamics that are easier to study theoretically. There is another assumption. The sequence of variance tends to a non-zero limit V star independently from the starting point VA. And we assume that the sequence of variances has already converged to V star. This assumption, I will discuss these assumptions in the next part. But at the end, we have a simple recurrence equation with a function C star, and we can distinguish three phases of information propagation: a chaotic phase where the inputs tends to decorrelate, an ordered phase where the correlations tends to 1 at an exponential rate, and the edge of chaos, that is an intermediary phase between the two, where the correlations between two inputs tends to 1, but at a sub-exponential rate. So all that can be computed only by using the function C star. That has been obtained because we have done two main approximations. And then we just have to tune sigma W and sigma B such that the neural network lies at the edge in the edge of chaos phase. We can represent it on a graph. So in function of sigma W and sigma B, we can compute the chaotic phase, the ordered phase, and on the black dotted line, it's the edge of chaos phase. So there is one thing to say about these results. At the edge of chaos, you have also a problem, because at the edge of chaos the limit correlation is always 1. So you cannot, there is no phase there where the correlations, the sequence of correlations CAB of L is completely preserved during propagation. It always tends to one limit that can be either 1 or 0 or something intermediary between 0 and 1, but you cannot have a complete preservation for any pair of inputs. It always tends to the same limit. So that's a limit, one of the limits of the edge of chaos. So now some experiments to illustrate some of the problems of the edge of chaos. So here we have some graph of correlations between inputs with different layer width. So n is equal to 10 and n is equal to 100 for ReLU and for 10H activation functions, and we observe CFBOL for several layer numbers L. So when we are using a very narrow neural networks with 10 neurons per layer, we see that in several cases the correlations do not tend to 1. So the theoretical prediction of the edge of chaos is not fulfilled in that case. And we have also some inconsistencies when we when we use wider neural networks. For instance, here for ReLU it doesn't tend to 1, and with ReLU with 100 neurons per layer, it tends to 1 more quickly than 10H. But it wasn't, which wasn't the case for n is equal to 10. And more importantly, you don't have Gaussian PreActivations. So here I've plotted the L infinity distance between the CDF of the Gaussian and the distribution of the CDF of the distribution of the PreActivations. So during propagation, so here you have on the x-axis the layer at which we can observe the distribution of the PreActivations. So for ReLU, it clearly doesn't tend to 0 in any case. So if it tends to 0, then it's approximately Gaussian. If it goes far from 0, it's not Gaussian. So we have a problem even with 10H with very narrow networks with n is equal to 10. But even with very wide neural networks, you still have a problem with ReLU. So even if you are making this heuristic thanks to the central limit theorem, but even with the very wide neural networks, n is equal to 1000, then you leave the Gaussian zone. So yes, and there is another limitation. The other assumption of the edge of chaos is that the sequence of variances tends to a single stable fixed point. This is a formal claim in the paper of Poole, but there is a counterexample that is these activation functions at the below. So this is a family of activation functions. So the activation function, you can see the shape of the activation functions in figure A, and in figure C you can see that it crosses an infinite number of times the identity. So the variance map has an infinite number of stable fixed points. So the claim above here by Poole is false. So that's another limitation of the edge of chaos. I won't say many details about that, but it's a common way unified way of seeing the processes of constructing initialization distributions. So it's about the preservation of some quantity that can be different according, for instance, to Gloro, it's the variance, the preservation of the variance. According to the edge of chaos, it's the preservation of the correlations. And we can find other invariances to find. And so many other initialization distributions are possible. So now our proposition of a solution to the problems that we have with the edge of chaos procedure, it's how to impose Gaussian PreActivations. So informally, we want to build an initialization distribution and an activation function such that in any realistic network, that is a finite network and not an infinite network with an infinite number of neurons per layer, so that in this network, the PreActivations are Gaussian at initialization. So here we are assuming that formally, we want to find a pair of P phi, where P is the initialization distribution of the weights, and phi is some activation functions. Here we are assuming that the biases are equal to 0 for the sake of simplicity, but we may think at Gaussian biases. It's not a problem. And we want that if you have Gaussian ZL, so inputs, then you end at the end at the output of the layer also Gaussian PreActivations at any layer. So once it's done for one layer, it's true for every layer. So here is the reduced version of the problem. So that's for one layer. So we want a sum of Wj phi x of j to be Gaussian. So to summarize the process of resolution of the problem, first we reduce the problem. So the problem can be reduced to this one. We want to find a distribution P, an initialization distribution W for W, and an activation function phi such that W times phi of x is Gaussian. As a sub-goal, we can replace phi of x by some random variable y, and we are looking for the distribution of y and W. We find constraints on P and Q, because if you want a product of random variables to be Gaussian, these random variables are constrained. You cannot choose anything as a random variable here. And we propose a familiar distribution for P that will be the symmetric variable distributions. And given P, compute Q. And when we have Q, we can compute the activation function phi. So the main difficulties here are to find constraints on P and Q, and to compute Q when P is known. So I will be a bit quick on the constraints. It's a bit technical, and I want to go to the experimental results a bit quickly. So for the constraints, first, if we want, so Z is the PreActivation, and we want the sum to be Gaussian. If the member of the sum are IID, then each term of the sum should be Gaussian. Is the first constraint we obtained, but I must say there is some simplification there about the dependencies between the PreActivations. It's something to include in the discussion about this constraint. So there is a constraint here about the density of the distribution of the weights at 0. I won't put too much details here. The only thing we have to keep in mind is that if you are multiplying two independent random variables, which both have a density which is not 0 at 0, then the density of the product will be infinite at 0. So we have some constraint over each of the variables w and y, such that z will be Gaussian, and in order to avoid an infinite density at 0. I won't talk about that. It's about some specific values of the densities. Here is an interesting part of the process of obtaining the constraints. It's about the tails of the distribution of w and y, and the tails must be light enough. So when we are gathering the constraints, we are choosing the variable the symmetric variable as initialization distribution for the weights in order to fulfill the constraints that we have put before. And once we have decided to take the symmetric variable distributions, there is a whole process of computing the Q. I will skip that. It's a bit technical. So at the end, we have this. So we have a whole family of initialization distributions in the graph A, which spans some kind of close to Rademacher distributions to some Gaussian with a 0 density at 0. And for each of these initialization distributions, we have activation functions in the graph C. So if you are close to Rademacher initialization distributions, then you have a bit close to identity activation functions. And otherwise, on the black curve, you have a close to 10H activation function. So now the experimental results. So I won't talk about the chromograph Smirnov test. It's about testing whether it's Gaussian or not. So for the first layer, we have in the process several numerical approximations. So obviously here, here we can see the curve means. So each point corresponds to the K-statistics of the distance between the preactivation after one layer, the distribution of the preactivation after one layer, and the Gaussian. So we want to be the lowest, the smallest possible. So we are roughly 10 times better than Relu and TANH that are, so Relu is in blue and TANH in purple. So we are much better, but still we have some effect of the number of inputs. What we have is not perfect. It can be improved. And we see that in the black case, so a very small theta, so phi theta and p theta with a small theta, is quite close to be Gaussian. Here is the same plot, but for 100 layers, and we see whether there is some drift after one layer of, or if there is some intrinsic problem in our numerical computation, so that it tends to 1. So the curves here show the distance to the Gaussian after 1, 20, 40, etc. layers. So in the narrow case, so with n is equal to 10, there are some of our examples that are much better than TANH, but some of them are also diverging in the narrow case. So there is some drift, and what we have is not perfect, and we can suspect problems in numerical approximations, but also in the independency assumption, as I talked about before. But yet, it's much better than the RLU, for instance, and it's better than tanh in several cases. We can plot the edge of chaos, so that's similar to the plot I showed before. But here it's exact in the sense where we don't have to do the infinitely wide neural networks approximation. And now some training experiments. So it's a bit, it may be a bit difficult to see, but we have, it's a LeNet, so it's a convolutional neural network for several sizes. I plotted the training loss in the first row and the test accuracy in the second row. So we see that in terms of training, there is the training goes well in any case. As in RLU and tanh, but there is some drop of accuracy for a bit wide neural networks here. So tanh and RLU are better in accuracy than our proposition. So we can discuss about that, but in the process of finding a good activation function and initialization procedure, it's all about the propagation of information and propagation of distributions. There is no, we don't have put any kind of constraint over the testing accuracy. It's all about the propagation of information and backpropagation. But in several cases, very specific cases with a very small number of neurons per layer, for instance, 3 or 10, the training loss, the training curves are quite bad for RLU and tanh in several cases. And we attain very acceptable losses with our activation functions. So in terms, in strict terms of propagation, for several of our activation functions, it propagates and backpropagates better than for tanh and RLU. So as a conclusion, we have shown some limits of the Gaussian hypothesis, especially for RLU. Shown some limits of the edge of chaos framework, especially with the existence of multiple stable fixed points for the VMAP. We have found a set of constraints that should be fulfilled to make the Gaussian hypothesis hold. We have found some family of activation function and initialization procedure. We have an exact edge of chaos that is an edge of chaos without the assumption of infinitely wide neural networks. And the training results are better in terms of propagation for narrow neural networks. But there is no clear results about the test loss. So there are some future possible works, such as including the dependency between the preactivations at the same layer. We can discuss about the generality of the constraints, such as imposing non-Gaussian preactivations. We can find other families of initialization distributions. We can study neural tangent canals with these kinds of the initialization distributions and activation functions. There is probably a way to take into account the generalization performance, for instance, by computing the first update and not only just the propagation, but also the backpropagation and the performance after one step. And maybe the most difficult in this case is this work about finding a way to keep the preactivation Gaussian. It's a way to avoid a problem that is much more difficult to solve, that is finding a very precise characterization of the preactivation distributions at initialization. It's very difficult. We know some things about the tails of the preactivations, about the concentration of the preactivations, but when we do propagation, it's very difficult to keep a very precise characterization of the preactivations. And is it desirable to have Gaussian preactivations? We did not answer this question here, but we have built a framework where it will be possible to make some progress on that question. Thank you. I hope it wasn't too long.
No, perfect. Thank you.
Are there any questions?
Yeah. Okay, let's see if there's any questions here. Yes.
Yes, I have a question concerning the slide 34. It's possible to return to it. 34.
34.
40, sorry. 34, yes.
Yes, so I maybe missed it, but which is the data set which is used to train?
It's IFR10, sorry. I forgot to say that. It's written at the beginning of the slide.
Yeah, okay, I just missed the information. And also,
sorry.
like, on the bottom right of like the bottom right graph,
Yes.
I'm quite concerned by the fact that everything seems to converge at the same value. So all the phi theta. How do you explain that?
Sorry.
Into plateau.
Mm-hmm.
Like all the
Yes.
phi theta seems to plateau to a converging value.
Mm.
How would you explain that?
I don't have any explanation for that effect. What we should keep in mind that it's a test loss here, or test accuracy. So I think it's not really about the family of activation functions here, but about some specificities of Relu and tanh here. For instance, for Relu, there is empirically, I would say that Relu, thanks to the zero part of the Relu, you can Relu itself has a generalization effect on the training. So I think there are some specificities of Relu and tanh that leads to better results here, and that doesn't happen with our functions. Maybe because none of them is bounded, and there is no way to cut information with our activation functions. I'm not sure it's clear, but when you are cutting half of the information with Relu, for instance, you induce a regularization effect. With tanh, you have two thresholds, soft thresholds, but you have thresholds. So I think we should think about these effects with Relu and tanh instead of the specificities of our activation functions.
Okay, thank you.
I mean,
Yep.
yeah, so I mean, it's more or less related, but in your results, so you have decided to only work with this class of functions of distribution. But so my first question would be, wouldn't it be better to work in the other way and to look at a class of acquisition function and then to find the distribution? Because I have the feeling that the acquisition function is a little more commonly acquisition. Oh, sorry. Activation function, sorry. So, and also it seems that you have conditions on your distribution, on your well distribution. So does it mean that you have also impossibility results for some classes of distribution?
That's true, and that's why we looked after first distribution, and afterwards, we computed from it the activation function. That's the reason why. For instance, putting phi is equal to Relu, for instance, would lead to an impossible result. It's impossible to get a Gaussian after using a Relu, for instance. So that's why we first fixed the initialization distribution, and afterwards computed the activation functions. And that's true. There are some impossible initialization distributions. For instance, the very used Gaussian initialization distribution cannot be used in that case. Because there are two effects. First, it's all about the first to this proposition. When you multiply two random variables, and these two random variables have a non-zero density at 0, then you have an infinite density at 0 here. So if W is Gaussian, then you must have a Y here with a 0 density at 0. And if you get that, then you have a very strange constraint of your activation functions, because your activation functions should transform a Gaussian into a random variable with a 0 density at 0. So this activation function would have an infinite derivative at 0. So there are problems with maybe. So I didn't even test these activation functions, but I assume it would lead to inconsistent results.
Okay, thanks a lot.
Thanks. I mean, I have a quick question. Well, hopefully quick. I think it's slide 35.
35.
Yeah, 35. Yeah. So right after. So this should be your results. Yeah, so yeah, there is one thing. So these are training loss, not test loss.
Yes.
So yeah, so you said that essentially. So these results show that your method produces a better propagation of information, and so why do you say that? In the sense that, I mean, an alternative could be that while using different activation functions, which probably in the large number of neurons, the activation maybe doesn't really matter. But let's say here I can say, well, maybe your activation functions are more flexible and they afford, to get a better training loss. So why do you think that's, say, it's better propagating information as opposed to just having a more flexible model? Because say maybe your activation functions afford a more flexible network.
I'm not sure to understand what you mean by flexibility.
I mean, let's say the flexibility as number of parameters, let's say, is not true, right? So let's say, so you're representing a function as a network, and by changing activation functions, you're changing the function that you can represent. And so let's say, so isn't that your activations are, let's say maybe cover a wider space of functions, and is that the same as being propagating information more efficiently? Because to me, it sounds a bit different.
Okay, so here. Just to remind that we are on NIST. Yes, that could be an explanation. I don't have any clear answer to your question. So I didn't do any computation about the size of the function space represented by my functions. So
yeah, because maybe essentially the fact that using these unbounded activation functions somewhat increases the, let's say, the flexibility of the representational power of your network, which maybe doesn't really matter if you have thousands of neurons per layer. Let's say here you're really restricting yourself to the range of small networks. So let's say that's exactly the situation which you would expect that the iteration function would really play a big role in depending in telling how flexible your network is. I mean, I don't know if this makes sense, but it really kind of
yes, I understand, but yes, that's a possibility. Maybe there is a way to test more precisely that hypothesis. Yeah, I will think about that.
No, it's just kind of seed I thought. Okay, yeah, thanks. It was super interesting and very, very intriguing. And I think we are out of time. So yeah, thanks again, Pierre. This was fantastic. Thanks.
Thank you.